Hey there, and welcome to the team. You're our newest developer, and honestly, you picked a crazy day to start. Right now, there is absolute chaos out on the grocery store floor. Angry customers are piling up at the registers. Store managers are literally pulling their hair out, and it's all because our checkout system is completely bugged out. Today's explainer is essentially a hands-on coding workshop. We're going to fix this terrible grocery store billing code using C++ operators. By the end of this, you'll see exactly how these fundamental building blocks of code actually work in a real-world scenario. It's going to be a lot of fun, so grab your digital tool belt and let's get to work.
Okay, let's dive into this. Why on earth did our grocery software just charge a poor customer $11 for a $10 item? I mean, it sounds like a ridiculously simple math error, right? Well, it's a bit deeper than that. Our compiler, who essentially acts as our digital cashier, is fundamentally misinterpreting the core instructions it's been given. To fix our cashier, we have to learn to speak its language. To do that, we absolutely have to understand operators. Simply put, these are the symbols that tell the compiler to perform specific mathematical, relational, or logical operations on your data. You can think of operators as the cashier's action verbs, things like scanning, adding, or comparing. The variables, like the actual price of a carton of milk, are just the physical grocery items that these verbs act upon. If you change the verb, you change the entire outcome of the transaction.
All right, here's our bug fix itinerary for today's workshop. We'll untangle the pre versus post trap, sort out our billing outcomes, figure out how to handle some complex customers, and finally, learn exactly why order matters. Let's start squashing these bugs.
Section 1. The pre versus post trap. Let's start with our first major bug. Imagine a customer brings an item to the scanner. The system is supposed to scan it, add it to the bill, and then increment the total count of items in their cart. But our system is doing this at the entirely wrong time. It's actually incrementing the price itself before the scan even finishes. That is what's causing that mysterious $11 charge for a $10 item.
The culprit here is exactly how we're using increment operators. These are unary operators, meaning they only need one single operand, just a single variable to work. But here's the catch. Putting the two plus signs before the variable, which is known as pre-increment, versus putting them after the variable, which is post-increment, completely changes the entire billing timeline. One acts immediately, while the other politely waits its turn.
Now, what's really interesting about this slide is the exact timeline of these operations. Let's look at the post-increment on the bottom row there. Starting with a value of 5, the system actually uses that original value of 5 for the current bill calculation first, and only after that does it update the stored value to 6 in the background. Pre-increment, on the top row, updates the value to 6 before it ever gets used in the bill. So our buggy code used pre-increment when it should have used post-increment. That's exactly why the customer was overcharged right at the register. But hold on, you can't just slap these plus signs anywhere in your code. You can only apply increment operators to an L value. Think of an L value, or left value, as a physical memory location. It's an actual storage box capable of holding real data, like a price tag. You absolutely cannot increment an R value, or right value, because that just represents a temporary math result or a constant. For example, you can't apply a plus plus directly to the expression A plus B, or just the number 5. The digital cashier needs a real, storable physical item to scan and update. Section 2. Billing outcomes. Okay, with that fixed, we can turn to our second bug. Right now, our checkout system is totally failing to apply the right checkout messages based on how much the customer is spending. VIPs are getting the regular, boring checkout message, and regular customers are getting VIP treatment. It's a complete mess. To fix this, we need to look at our relational operators. Think of these as our software's bouncers, or gatekeepers. We've got equal to, not equal to, less than or equal to, greater than or equal to, less than, and greater than. What these do is compare two separate values to find their relationship. And the absolute beauty of relational operators is that they always boil a really complex comparison down to a simple, clean, Boolean answer. It's either true or false. There's no gray area here. You either pass the gatekeeper or you don't.
Let me show you the exact scenario from our source code. We have a VIP threshold of 300 points. A customer checks out with a massive 2090 points. We use the greater than or equal to operator, so is 2090 greater than or equal to 300? True! So the system prints, bingo, you are in! Now, if the condition returned false, the system would jump to the else condition and print, oops, you are out. Our bug? The original developers simply used a less than sign instead of a greater than sign. Literally one tiny typo causing one massive headache. But boom, bug number 2 is officially squashed.
Section 3. Complex Customers. Moving right along our itinerary. Our store just introduced some really complex discount promotions for the holidays, and the current code is practically crashing because it simply cannot handle evaluating multiple conditions at the exact same time.
So, here's the challenge we're facing. How do we check if a customer is a VIP and they also bought milk? Or, like we see in some system validation checks, what if we need a customer's card ID to be divisible by 2 and 3 simultaneously? We need a robust way to combine our relational true or false checks into one master decision for the cashier to follow. And this brilliantly illustrates why we have logical operators. They combine or reverse Boolean values to make complex decisions. The logical AND, which is represented by 2 ampersands, is super strict. It requires all sides to be true. The logical OR is much more relaxed, requiring only one side to be true to pass. And the logical NOT simply acts as a switch, reversing the final true or false result, turning a true into a false and vice versa. Let's look at the logical AND in action to fix our holiday discount bug. Say condition 1 is true. The customer did indeed buy the $30 milk. But condition 2 is false. They are not a VIP member. Because we used the strict logical AND, a single false instantly rejects the entire discount, resulting in false overall. Both conditions must be absolutely true for the AND operator to let them through. This matters because it strictly protects the store from giving away unearned discounts to just anybody who happens to buy milk.
Section 4. Order matters. Okay, we have arrived at our final challenge. This is our final boss bug. A massive checkout bill is outputting totally random numbers, the math is entirely wrong, and the store is literally hemorrhaging money. The underlying issue here? Mixed operations.
Just look at this equation right from the broken code. Bill total equals X plus Y times Z. When adding and multiplying happen on the exact same line like this, we as humans might naturally just read it left to right. But the compiler, it gets utterly confused on what to do first if we don't have clear, established rules. Without a solid plan, the cashier basically just starts mashing buttons.
So, the crucial point is that the compiler naturally resolves this by checking its built-in rules. It first checks precedence levels. It sees that multiplication ranks higher than addition, so y times z is calculated first. After that multiplication is totally complete, x is added to that mathematical result. C++ has a strict pecking order known as operator precedence. It's exactly like the BODMAS or PEMDAS rules you learned back in standard math class, ensuring everyone gets the exact same total every single time.
But wait, what if 2 operators have the exact same precedence level, like say a multiplication and a division back to back? That is where associativity comes in. It's the rule, either left to right or right to left, that decides which operator goes first in a dead tie. It essentially acts as the ultimate tiebreaker for the compiler's reading direction, ensuring the math is done perfectly and consistently.
Well, congratulations! You have successfully fixed the grocery checkout system. You've mastered arithmetic, relational, and logical operators to save the day. And let me tell you, the store managers are thrilled. But what happens when the grocery store scales up and wants to calculate bills at the foundational binary bit level, just to save memory? How do we shift zeros and ones directly using bitwise operators? Well, that is a whole new puzzle, and we will crack it next time. Thanks for joining this explainer. I'll see you in the next one.
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos are coming soon.